669 quintillion, 741 quadrillion, 939 trillion, 156 billion, 986 million, 542,519. This number encodes my name. I'll explain how it does that. Prime numbers, of course, always come between another prime number and a previous prime number. At least that is, other than the number 2, which we're not going to worry about. This is the gap to the next, and this is the gap to the previous. You could think about this, the prime number, the target prime number, whatever it is, to move in a box between the next prime number and the previous prime number. In other words, as you count through a sequence of prime numbers, you could think about the current prime number to be in some relation to the next prime number and the previous prime number. If you take the next prime number and subtract the previous prime number from it, you get something called the second difference. Second difference is a number. It's positive when the next prime number is further away than the previous prime number. It's negative when the previous prime number is further away than the current prime number. In the list of prime numbers, there are only certain second differences that occur right away. In other words, there's up to the first 100,000 prime numbers, there's only 96 distinct second differences which occur. They're always even, and they're a number that is positive or negative. Looking at a list of second differences, here we have the first few prime numbers starting with 3, 5, 7, 11. The second differences are 1. For 5, it's 0. For 7, it's 2. Difference between 4 and 2. 11, it's -2. 13 is 2 again. And you can see there's a lot of 2's. There's a -4 and then a 4. More 2's, then 0, then 4's, then 2, then 2, then 4, -2, -4, 2, -2. And then it's not until 113 that we get a 10, a different second difference. And then we get 8's, 4, 0, 2, 2, 0, 6. Notice whenever it's 0 after 5, it's always a 6 or a multiple of 6 on either side for the previous gap and the next gap. But you can see that some second differences are much more common than others. If you look at many of these going along, you'll see that in the early small primes, 2 is very, very common. Here's some more. When we get into mid-level primes, this is a 512-bit prime. And some of the second differences we're seeing here, -756, 108, 194, -586, 302, -42. There are still certain ones that are going to be more common than others, but there's a lot of more variety in the second difference. And here we have some ridiculous 8,000-bit prime. That's the prime. And then in this neighborhood, the kinds of second differences we're seeing are 15,000 negative 16,000, 15,180, negative 13,000. Here's 706. But you can see that the sequences that happen are very determined on what neighborhood you're in when you're looking. I was interested in finding a way that you could compare neighborhoods anywhere. So again, when we have a prime, the next prime, previous prime, we can take these gaps, previous gap, and rather than just taking the difference between the next gap and the previous gap, we also take the second sum. We add up these things. So we get the next gap minus previous gap over next gap plus previous gap. And this we call second ratio. At least that's what I call it. I don't know what anybody else calls it because I couldn't find anybody else talking about it, whatever that means. When we do this, we get a number that's always between -1 and +1. And it might also be 0. This is a ratio. When we take a reduced fraction, it's very easy to compare prime numbers anywhere across the spectrum. So, for example, the most common second ratios stay more or less the same, although they're not as common as you get higher and higher into the spectrum of prime numbers. This is an image without labels of the first million prime numbers. See how nice and symmetric it is. And these longest lines here and here are positive 1/3 and minus 1/3 over here. This is positive 1/2, minus 1/2. This is 0, straight down. So this is a graph where we, by multiplying by pi, that number that's between -1 and 1, it plots very nicely on a circle. The length of the line is the occurrence, the number of occurrences of that particular second ratio in the data set. You can see that there's little gaps in between, and again, because this is the low primes, this is only the first million primes. When we look at this, this is a plot of the 1000-bit primes. And so here, although the most common primes are still the same second ratios, the lines are smaller relative to the number of lines that are very short on the inside. So there's many more of these uncommon second ratios than there are in the first million primes. And this is that 1000-bit prime neighborhood showing the most common out here and then superimposed with all of the other ones on the inside. So there's a combination of the labels and the non-labels, because putting labels on all these things in the middle, you couldn't read it. So what I have done in order to make my mega number is to take these second ratios and map them onto letters, saying that the most common second ratios, we're going to call them, match them up with the most common letters in English. And I end up in a sequence of primes. I end up with stuff that looks like this. Now originally I really wanted to be able to find sentences and to be able to give an address with a prime and a length of a data set and a length of a string, and be able to say with the most common second ratios in this data set, match them up with the most common letters in English, and then go to this prime, and for some run, I would give you something that would be a sentence. A brick brown fox jumps over the lazy dog. You know it. But I could not find all those words. And I realized that in order to use this as a cipher, it would have to be a much more elaborate way of converting these somewhat random but also structured by the properties of prime numbers, these sequences of text. But what I did do is find my name. So here, my criteria was I was looking for a word and it needed to be surrounded by spaces. The spaces are encoded by second ratios, which are less common than the more common 75% second ratios, which map onto letters. So anything that doesn't map to a letter is a space. And I was looking for Tem with spaces around it. And I found that at 4,186,907, a prime number. That's the starting. 4,186,937 is the ending prime of this word Tem that maps by second ratios to Tem. And then Noon I found at 2,385,113, and the last N at 2,385,157. And when you multiply those two numbers together, those four numbers together rather, the prime factors that come out lead to this number: 99, 727, 669, 741, 939, 156, 986, 542, 519. So that is my mega favorite number. And this is how you can use prime numbers to map to letters, though not very well. It is a work in progress, but that is my mega favorite number.